Our project title is Experimental Study on Self-Curing Concrete Using Sodium Lignosulphonate, present by Durai Priyadashini, K. Kalevani, M. Kingsta Butlin. Our internal supervisor is Mr. Riaz Ahmad, ME, Assistant Professor, Civil Department. Abstract. Concrete is a mixture of cement, aggregates and water with or without suitable admixtures. Curing is the process of maintaining the proper moisture content to promote optimum cement hydration immediately after placement and to attain desirable strength and other properties. This paper reports an experimental study carried out to investigate the compressive strength and split tensile strength of self-curing concrete using sodium lignosulphonate as a self-curing agent in varying percentages 0.5, 1, 1.5, 2, 2.5 and 3% for 7, 14, 28 days are analyzed, tested and compared with conventional concrete of similar mixed design. According to IS 10262-1982, the mixed design is determined for concrete of grade M20. Compressive and split tensile test results show that the optimum strength of a self-curing concrete attained at 0.5% mixture of sodium lignosulphonate when compared to conventional concrete. Introduction. Construction industries is growing day by day even in remote areas and desert regions. Even India and other countries are facing lots of problems in supplying drinking water to their citizens. Hence, construction industries are under pressure in finding out alternative curing methods of concrete. Self-curing concrete is one which can meet the present and future requirements of curing concrete. What is self-curing concrete? Self-curing concrete is the one which can cure itself by retaining its moisture content. A concrete can be made to self-cure either by adding curing admixtures or by the application of curing components. There are two methods of self-curing concrete. One is external self-curing of concrete, another one is internal self-curing of concrete. In this project, we adopt internal self-curing of concrete. Internal curing of concrete. According to ACI, the internal self-curing is the process by which the hydration of a cement occurs because of availability of additional internal water. Material used in this project, we used cement, fine aggregate, coarse aggregate, water and self-curing admixtures. Cement, we used 53 grade of ordinary Portland cement. Fine aggregate. Fine aggregate used was obtained from nearby sources. Coarse aggregate. Crushed stones was used as a coarse aggregate. Water. The water used was fresh, colorless, odorless and tasteless potable water that was free from coarse, yearly aged cracking organic matter of any type. Self-curing agent used. We used sodium lignosulphonate as a self-curing agent. It's a mixture of lignosulphonic acid and sodium salts. It's a water reducer and it's mainly for concrete mixtures as water reducing additive. The sodium lignosulphonate is fit for apply to building projects, dam projects, throughway projects, etc. Sodium lignosulphonate is economical one for a brick projects. Uses. Ready-mix concrete where workability retention coupled with retardation of initial set is beneficial. Water reduction significantly improves compressive strength at all ages, enhances durability through the production of low permeability concrete, reduces placing problems in hot weather concreting by improving workability and workability retention. Chloride free, safe for use in pre-stressed and reinforced concrete, allows workability to be increased without adding extra water. These are the properties of sodium lignosulphonates. Need for study. Can reduce 10% of water consumption at least. Can improve mixture of the concrete. Compressive strength improves by more than 15% equally on 3 to 28 days. Have no function of corroding on the reinforcing bar. Objective. To improve the effectiveness of the water content of the concrete mix. Second one, to determine the characteristics of a self-curing concrete such as compressive and split tensile strength by adding self-curing agent in varying percentages. Third one, to compare the strength between conventional and self-curing concrete. Methodology. First, we collected literatures, Then we collected materials when we conducted a lab test, that's a specimen test and material test. Then we analyzed the results of a specimen test and material test. Finally, we got the conclusion of this project. These are the literature study we collected. First one is self-curing concrete. It's a journal. In that journal, they added 0 to 1% of polyethylene glycol 400 by weight of a cement for M20 grade concrete. From that, they found 1% of a polyethylene glycol 400 by weight of a cement was optimum for M20 grade concrete for achieve maximum strength. Second literature, self-curing, self-compacting concrete. Material test. We conducted two material tests. One is specific gravity and sieve analysis. First one, specific gravity. The specific gravity test was conducted for fine aggregate, coarse aggregate and cement. Fine aggregate. We got the value of a specific gravity as 2.636. For coarse aggregate, the specific gravity value is find out as 2.645. For cement, it's a find out by 3.478. Sieve analysis. Sieve analysis is conducted for fine aggregate and coarse aggregate. These are the values obtained from the sieve analysis test of fine aggregate. From that, we plot a graph. From the graph, we find out the coefficient of uniformity as a 3.24, coefficient of curvature as 0.96. Sieve analysis for coarse aggregate. First, we take 2 kg of a coarse aggregate. From that, we conducted a sieve analysis test and we got these values from that. Finally, we calculated the percentage of a flakiness index as 0.9%. Mixed design. The mixed design was conducted as per IES 10262/1982. The compressive strength required in the field at 28 days is 20 megapascal. The maximum size of aggregate we used is 20 mm. The test data for materials: specific gravity of a cement is equal to 3.478, specific gravity of coarse aggregate is equal to 2.645, specific gravity of fine aggregate is equal to 2.636. First, we calculated the target mean strength of concrete. From the formula, M20 plus 1.65 into 4. 1.65 is a T and 4 is 4. 4 is S. It's taken from the IS code 10262/1982. Then we calculate the selection of water cement ratio. From that, using a target mean strength, from figure 11.10, the water cement ratio is find out as 0.5. Selection of water and sand content. From table 11.24, IS 10262/1982, for maximum size 20 mm grade concrete, 20 mm aggregate and a sand conforming to grading zone 2, the water content per cubic meter of a concrete is taken as 186 kg and sand content as percentage of total aggregate by absolute volume is equal to 35%. For change in the value in water cement ratio, compacting factor for sand belonging to zone 3, following adjustment is required. For V, the adjustments are got: percentage adjustment required for water content is plus 3. The percentage adjustment required sand in total aggregate is equal to minus 3.5. Using that, we calculated the water content as 191.61 per meter cube. From the water and water cement ratio, we got the cement content as 383 kg per meter cube. We find out the cement content. Now we are going to find out the coarse and fine aggregate content. Using these two formulas, from IS 10262-1982, the fine aggregate and coarse aggregate volumes are calculated as 620 kg, 1171 kg. Then we adopt the mixed proportion as 1 is 1.5 is 3, that is M20 grade concrete. Slum cone test. Slum cone test is used to find out the workability of a concrete. We conducted a slum cone test for a conventional and self-curing concrete. From that we got these values. In this project we got the 0.5% of a self-curing concrete is optimum. For that we got the slump value as 130 mm. Using these tables, the result of a slump test, we got that value 130 mm for the percentage of sodium lignosulphonate 0.5%. For that value we got the workability is very high. Compressive strength. We conducted a compressive strength for 7 days, 14 days and 28 days for conventional and self-curing concrete. We got these values from that test we conducted. From these values we got the optimum value at 0.5% of sodium lignosulphonate, which is self-curing concrete. 7 days 14.44 Newton per mm square, at 14 days 18.22 Newton per mm square, at 28 days 24 Newton per mm square, which is greater than a conventional concrete. This is a comparison chart of the self-curing and conventional concrete. Split tensile strength. It's an indirect method of a tensile strength. We conducted a split tensile strength in a concrete lab for 7 days, 14 days and 28 days. The split tensile strength was conducted using a cylinder, concrete cylinders. From these also we got the optimum value at 0.5% of self-curing concrete. 7 days 1.62 Newton per mm square, 14 days 1.73 Newton per mm square, 28 days 2 Newton per mm square. This is a comparison chart of split tensile strength of conventional and self-curing concrete. Conclusion. Experimental studies were carried out on concrete by adding self-curing agent in varying percentage of cement. Physical properties such as compressive strength and split tensile strength was evaluated based on the experimental result. That the following conclusions are drawn. The self-curing agent of a sodium lignosulphonate is used at different percentages with M20 grade concrete mix and analyze the result. It reveals that the compressive strength of a concrete is found to be increased by 6.25% at 0.5% of sodium lignosulphonate compared with conventional concrete of same water cement ratio. To check the tensile strength, split tensile test is conducted, which shows that the strength increased by 2.5% at 0.5% sodium lignosulphonate to conventional concrete with same water cement ratio. Comparing to these varying percentage of sodium lignosulphonate, 0.5%, 1%, 1.5%, 2%, 2.5%, 3.5%. A compressive and split tensile test result shows that the optimum strength of a self-curing concrete attained at 0.5% mixture of sodium lignosulphonate when compared to conventional concrete. The experimental study shows that the use of water-soluble sodium lignosulphonate is possible as self-curing agent. It reduces placing problem in hot weather concreting by improving workability and workability retention and allows workability to be increased without adding extra waters. These are the references of our project. Thank you.